Immersive media is one of the killer applications on the internet and telco networks. For example, metaverse, AR, VR, and cloud gaming. It is a known challenge to stream and broadcast immersive media content over public network, especially 5G wireless network, due to the constraints of bandwidth and latency. Hi, my name is Shen. I'm from Intel Network and Edge Group. Today, I will use 360-degree video as an example to analyze the bottlenecks in the technical stack and present our efforts to bring immersive experience to the user. To successfully deliver immersive media over the network, we need technologies from different domains. From the top to the bottom, those technologies can be roughly grouped into three layers. Media processing. In this context, it is about compress and organize the media content into a data structure that can be easily transported and accessed through networks. There are existing video codecs that can be used to compress immersive media content like 360-degree video and volumetric data. It is important to note immersive media may need more flexible ways to access partial contents in the 3D space. The media transport, just like other type of data, most video contents today are delivered by TCP, HTTP-based transport protocols. However, HTTP and TCP protocols are rigid in congestion control and packet retransmissions. That could be overhead for immersive media transport because not all contents are equally important. Network infrastructure, it is a fundamental layer for network transports. As we know, even for the 2D video streaming, the network topology where the CDN is located is critical for the transport latencies. Edge server defined by telco industry can intelligently utilize wireless quality of service for media streaming, and it can also greatly reduce the interactive latency by being closer to the client devices. Now, let's take the vertical view and see how to build a holistic solution to deliver 360-degree video broadcasting. 360-degree video is a simple version of VR. The user's viewing perspective is from the center of the sphere looking outward. It supports 3 degrees of freedoms. Users with HMD can look left and right, up and down, and pivot left and right, but they cannot move throughout the virtual space. Each frame for 360-degree video is projected to a 2D rectangular so that it can be compressed by video codecs. Furthermore, sees the content only within the viewport. The viewport-dependent streaming can save a lot bandwidth. To support this viewport-dependent streaming, the video codecs will need to support tailing to segment the full view content into smaller pieces and packing to pack video content with a lower resolution of the full view. You may find more details about 360-degree video in MPEG-I OMIF standard. With tailing support in video codec, bitstream rewriting can be used to quickly pack the tails for any new viewports. However, there is still a big challenge during the viewport switch because of the temporal dependency built into video compression. Look at the bottom diagram, which is a sequence of frames in the viewport-dependent streaming. At the beginning, the viewport is at the center of the frames. When the viewport switch happens between the second and the third P frame, the tails in the new viewport in the orange color is not decodable in the receiver devices. In this case, we can only scale up low-resolution tails and make up for that position until the next iframe comes. So in viewport-dependent streaming, MTHQ latency, motion to high-quality latency, is evaluated, the usual MTP motion-to-photon latency can be satisfied by using the low-resolution content. Then we come to the media transport layer. We can easily find this kind of comparison between RTC and HTTP-based transport in many papers. HTTP-based transport do have advantage in terms of deployment and scalability, but UDP-based RTC protocols, for example RTP, are very good for low latency transport, which is necessary for immersive media. Moreover, it is much easier to extend congestion control algorithms in UDP-based protocols. So RTC is critical for both immersive media and 5G network. Now we select WebRTC to be the transport for making viewport-dependent streaming and for 360-degree video. In this diagram, we can see there is a constant exchange of viewport information and viewport content between client and the server. The WebRTC client will constantly send the viewport information to the server. The WebRTC server will pack the high-resolution tiles for the given viewport plus the full-view low-resolution content all together into one frame and send it back to the client. Now we have figured out media processing and media transports. Finally, we will deploy this application in certain network infrastructure. There are a few factors to consider when we deploy this application. If we place this application in the cloud, in the data center, the one-way latency is about 100 milliseconds, so the viewport exchange for the 360-degree video will take at minimum 200 milliseconds in the round trip. If we place this application on the on-prem network, we do get much better latency. However, we will get difficulty to scale this application to the large region. So to trade off those factors, then we can select the technical edge as the place to deploy this application. And in the edge server, we can also benefit from the 5G quality of services. To put everything together, we come up with this end-to-end WebRTC-based AK360-degree video broadcasting solution. In this solution, we separate media functions into three pieces. The media ingestion function and also media distribution function will work with 5G UPF, the user plan function, that reset in the edge servers and co-locate with 5G RAN. The media ingestion function will handle multiple camera inputs and provide 360 video stitching and encoding. Media distribution function will handle viewport packing and viewport switch based on each client's feedback. There is a media control function in the middle. It will provide signaling and orchestrations for different devices, including camera and receiver devices, to join the broadcasting. Media control functions can be placed on the public network. Here comes the demo video. In this demo, we have two 360-degree camera and three Android phones as a receiver. First, we place one camera in a remote room. In the server room, we have 5G core 5G RAN plus all the three media functions as we defined in the previous slide. On the receiver side, as we can see, we have three Android phones. On the right, the two Android phones receive the content from the camera, the first camera in the other room, And also we have another camera in this room just for the end-to-end testing. So the Android phone on the left is receiving the content from the camera on this table. And on the back of the room, there is a 5G transmitter to support the wireless connection. Okay, based on the implementation and the measurement, we got significant good results. For the glass-to-glass latency, we achieved 1.3 seconds, and in the comparable HTTP-based solution, usually that will take more than 5 seconds. The media processing during the entire pipeline takes about 0.9 seconds. So we can achieve much better latency by improve this media processing using hardware acceleration. The MTHQ latency is the second latency we measured in this implementation. The MTHQ latency is the viewport switch latency, and is in this implementation we have 200 millisecond, which is way better than the comparable CDN and HTTP-based solutions. In the latency breakdown, we can see the media processing is still the largest bottleneck. The temporal dependency, the gulp size in the codec will cause about 40% of this interactive latency. We had new solutions to reduce this MTHQ latency. We designed a new coding structure based on scalable video coding to remove the gulp size, the gulp structure completely from this interactive latency. Secondly, we used time series analysis to predict the next viewport so that we can prepare the contents in advance. Our solution is one of the prototypes in the ecosystem. There are many significant developments in recent years. With regards to media processing, new video codecs AV1, VVC start to consider immersive media contents that are beyond traditional 2D videos. 3D volumetric codecs like VPCC, GPCC are coming to the market as well. As for media transports, new transport protocols, QUIC and HTTP3, are tailored for media streaming. Especially L4S provides a new mechanism of congestion control, which can significantly reduce end-to-end latency. In the infrastructure layer, the telco industry has defined XRM, extended reality services. Like what we have seen in the demo, the immersive media engine and services now can be running in the user plan of a 5G mobile core to achieve low latency. And this model also supports the device and wearables less expensive or with preserved batteries. In addition, in this model, the network layer can be aware of the importance and the correlations of video packets so that it can give much more efficient traffic handling. All of this will pave the way to reduce the end-to-end latency and improve visual quality for the immersive media over the 5G network. Now let's summarize today's presentation. Large-scale immersive media broadcasting is possible with today's network capability of 5G and edge computing. Media processing performance is still the bottleneck for the user experience. To create truly immersive experience, collaborative cross-layer innovation are expected. In this implementation, we identified key building blocks and demonstrate a scalable RTC as a service for immersive media applications. In the future, we plan to support more immersive media data formats and to incorporate new technologies from different domains, especially network AI and media AI, to accelerate the delivery of immersive media over 5G network. Thank you. This is my contact information.